Let me introduce to you the Global VR Challenge winner from last year, and a friend of mine, Tristan. He's going to be talking about performance optimization in VR, and yeah, leave it to you. Give me a round of applause.
Can you hear me okay?
Yeah.
I'm getting over the E3 sickness, so I apologize for that. My talk is a little bit more specific than a lot of the ones that I've seen here today, so hopefully it doesn't scare any of you off. I have a lot of content in here, and I just want to make sure that I can get through it all, so we'll see how it goes. I'd originally thought I had an hour. So I'm Tristan Parrish. I'm the designer, writer, technical artist, and creative director for Broken Window Studios, which is the company I founded with my wife, Abby. And then also I'm the creative director at Timefire VR, where we just released this Chronic Hypatia, which is an MMO VR experience. So basically I wear a lot of hats, and I have a lot of experience with content optimization as well as with the design process. So one thing I wanted to note for anybody who's looking at this is primarily discussing desktop VR. So there are definitely a lot of rules that generally apply to all platforms, but to make sure that I was able to give useful information, I wanted to focus on desktop VR primarily. So some of the numbers are going to be a little bit different. But you can think in general, if you're following these kind of rules, you can apply them more aggressively if you're on mobile or console, and it will work just as well. So rule number one, and this is if we're talking about optimizing performance issues in your VR product. If you're having trouble with performance, it's almost always art. And no, I'm not saying this to throw blame around or anything like that. But the main reason it's important to note is because I've worked on a number of teams where when content optimizations need to happen, they actually pass it off to the engineering team to try to solve those problems and say, oh, hey, can you write a script that combines our assets together or optimizes poly counts or something like that. And I think that in general, that's a bad philosophy to follow when you're working on content optimization because our content really is at the source of a lot of those kind of performance issues, and it would be best to go back to the art side and fix art rather than trying to say engineers who already have too much to do should go and try to figure out ways to optimize other people's content. So that's why that's rule number one for me. Rule number two, fix content problems by fixing the content, not by using engine features. So this is kind of extending off of the idea of rule number one. So if you're asking your computer to do more work to convert your content into a more performance-friendly state at runtime, just stop and do it yourself. This is basically saying fix your assets on the content creation side, not on the end user runtime side. And so there's a lot of types of tools that you can use. There's things like occlusion culling, static batching, dynamic batching, mesh simplification, mesh combiners, GPU instancing, custom LED solutions, etc. You can go through a long list of possible things that could be used to improve your performance. But these should not be your immediate go-to when you see content problems. You should always be looking at the content. So the exception to rule number two would be that sometimes you can actually find tools that are useful for improving the content at the authoring phase. Examples would be texture atlasers, mesh combiners, substance, tools that basically make your content creation workflow more effective. Those are things that I would definitely advocate using. But they don't happen at runtime, so they don't have a performance cost associated with them. Just as a general statement, I want to make sure that everybody feels the same way I do about optimization, which is that optimization is for producing better graphics. Every game that looks brilliant is a game that has been super well optimized, both on the engine side and on the content production side. And so optimizing is not to make something look worse, it's to make it look better. And there's also games that were poorly optimized that actually suffered quite a lot, especially in the negative perception from users, like Arkham Knight by Rocksteady, simply because they didn't have good optimization. And that's a huge waste of a huge amount of effort that goes into that production when somebody feels like they just can't play it well. So what are some good values for VR? This is always going to be ambiguous because it does depend somewhat on your content and all the varying platforms that are available. But as a general rule, you have to hit 90 frames per second, which is an 11 millisecond frame time. you have to have between 1 and 2 million triangles as an upper limit, and you probably want to be within 500 to 1,000 draw calls. So these values are consistently reliable. I think if you hit all of these numbers, you're going to have a pretty well-performing VR game. And you can push 1 or 2 things, but what you really can't push is your frame rate. So rule number 3 is learning and using your profiler. So I don't know, a show of hands, how many people here use Unity? Anybody using Unreal? I see one over there. Let's see, half hand. So I've used both. I actually prefer Unity, but I think that a lot of people ask questions about content optimization, and the first thing I ask them is like, well, how many triangles are you rendering in a frame? Or what are your draw calls? Or how many objects do you have? What is your memory usage? And a lot of them have actually said they don't know, and that to me is the initial red flag. So if you want to optimize your game content, there are some incredibly, incredibly valuable tools built into modern engines that allow you to profile that information. Unity's profiler has definitely saved my bacon a bunch of times, and it really gives you a ton of information if you learn to read it. So I'm not a programmer by initial profession. I do some programming, but I would say that even laymen can understand the profilers if they just give them a little bit of time. So it's very important to do so. Also, don't try solving problems you don't have. I notice a lot of people will say, oh, I heard on a talk somewhere that this is the thing that I need to watch out for to make my game more performant. And if they do that and then they just start making changes that don't actually apply to their content, they're going to see no performance gain, and they're not going to know why. So that's one of the reasons profiling is so important. So profile builds, or in Unreal 4, a standalone game. Close all your other applications to free up your hardware. And if you're unsure about causes, make isolated changes. So change one thing that you see as a major culprit, and then profile again. I don't know if anybody ever watched that show, but are you CPU bound or GPU bound? This is actually one of the really important questions to ask when you're profiling your performance, because the 2 pieces of hardware will only run as fast as the slowest piece. So if your CPU is taking more time than your GPU, you're actually going to have a GPU that is just waiting for your CPU to finish. The same is true in the reverse, and most profilers will actually specifically indicate that, like CPU stall or wait for GPU or something like that. Generally, the main difference between these two is the CPU is going to be doing the heavier math stuff, and I don't know, I think I had to cut that slide out. The CPU is going to be doing more of the math stuff, like the things that are runtime computation, actually fetching models from memory and handing them over to the GPU. And the GPU is going to be doing all of the number crunching for polygon counts, actual pixels on the screen, etc. So, mesh complexity. This is one of the big components of performance optimization in VR. Is looking at the data that you're pushing to the GPU with your meshes. So that's going to be the triangle count, vertex count, vertex colors, bones, and animation data that are actually stored in your 3D models. And so as you can see here, there's kind of the wireframe for that character, and that's a fairly dense character. That's from our game Reflections. Generally, triangle counts and vertex counts can both be used reasonably to figure out how complex is your model, but vertex counts are technically more accurate because you get more information about UVs, shading splits, etc. And vertex counts can occasionally diverge quite a bit from triangle counts, and that's usually a sign that your models may have something under the hood that's less optimized. But so myth number 1 for VR is that your scenes need to be more detailed in VR than in non-VR games. Now that seems kind of intuitive, but the reality is that your VR app has to be 2 to 4 times more optimized than an equivalent VR project. And so if you don't believe me, let's talk about that for a second. This is what a standard game would look like. 60 frames per second, 16 milliseconds frame time, monoscopic, meaning you're only rendering the screen once, and the field of view is about 50 to 90 degrees, so there's not a huge amount of objects that are on the screen. When you're looking at a VR game, it's going to be 90 frames per second, which is actually 11 milliseconds for the frame time. It's stereoscopic, meaning you have to render this scene twice, and the field of view can be usually around 110 degrees, but it can actually be more on some upcoming hardware. So based on this information, it's pretty obvious that our VR game has to be more optimized than the exact same game if it weren't in VR. So rule number 4 is basically assume your content needs to be 1/3 as complex as an equivalent PC title. And this is not just mesh complexity, but for all aspects of performance. It's actually interesting because it feels in some ways a little bit more like the shift from console to mobile than it does going to a more advanced PC architecture, because you can't really take advantage of the hardware as much as you might initially think that you can. And so just to help kind of clarify that, I use a metaphor of a glass. So the things that you're trying to put into your game are filling this glass, and this glass overflows at your frame time, the cap at which your frames would start to dip below 90 frames per second. And so as you add things, like 3D models, that seems fine, and you'll never look at your initial 3D models and say, oh, there's no way that that's going to be too bad. But then you start adding in lighting, and then you start going in with your characters and animations, and then you add your particle systems, and then your gameplay and physics, and by the time you get to the end of all this, you're way over the line on what you actually can run on your game. So it's extremely important to look at this from the very outset and not say, oh, I have this one 200,000 poly model, but that one model seems to be rendering fine. I'm sure it'll be okay when I'm done. Because by the time you're at this point, where you're overflowing, the table's getting covered with water or whatever it is, you're going to have a harder time optimizing than if you did it in the first place. So myth number 2, normal maps don't work in VR. I think this is the second time Michael Abrash is being mentioned in this room today. But Michael Abrash said in 2014 that normal maps often don't look good. And I think a lot of people who heard this went on to say, oh, normal maps don't work in VR. And so normal maps can not do as good of a job faking geometry in VR, but they are still essential for contour information and overall surface smoothness on your models. And every high-end commercial VR game that I've seen uses normal maps today. So while I think that the intention is very important for the statement that normal maps don't do everything they used to, they still do a ton. And so here's a comparison. This is an example of what would be a bad usage of a normal map, because there's too much detail in the high res and too little detail in the low res. This is an example of where normal maps can be very well used, which is from our game Grave. We have the low poly wireframe, the high poly normal map, and then the final material. Simon, do I have a little bit of extra time?
Yeah, fine.
Okay. Simon told me I could have more time because we're running fast. So most VR games also are rendered with PBR shaders. And because PBR uses a lot of image-based effects or reflections of the environment, having a normal map on a surface actually makes it easier to get more credible visuals than you would without one. And I'm sure you can see here on the left is the one with the normal map from a high poly source model, and then on the right is the, you see obvious hard edges, UV splits, mushy reflections, kind of distortion all over it. And that's because there's smoothing groups on the low poly model. So LODs in VR are extremely important because you want to make sure that objects that are far away are not taking up as many triangles as the objects up close. This is a good way to optimize so you can still have objects that are close to your hand that look detailed, but that aren't detailed very far away. The one thing that's important to note about LODs in VR is that you probably have to have them transition at 2 or 3 times the distance that you would in a normal game application, because the screen percentage is much smaller in VR than it would be in a normal game. If you're using LODs for a character model, there are generation tools available, so like Simply Gone or things like that can actually work. If you're making LODs for hard surface models, just make the LODs manually. Just tell your artist to do it. I know they won't like it, but you should have them do it anyway. There's no good way to make hard surface models simpler with a tool. Occlusion culling is also very useful. And one thing I'll say about occlusion culling is that actually in Unreal Engine, static occlusion culling performs better than the dynamic real-time occlusion culling. So you want to make sure that you're always using this on any of your VR projects. Occlusion culling is not enabled by default in Unity, so you have to make sure you add it in. And then also, if you want to make your occlusion culling more optimal, you can use visibility blockers. Basically, the idea is that you have a scene, and then you want to make sure that it's very, very hard to see through any gaps in the models in the scene. So you just put some geometry that either is set not to render or has like a null material on it, so that you can have that still block visibility, but actually make the checks much simpler. Terrain is your enemy, so you got to be really, really careful with terrain. This is a shot from Bloodborne. I just wanted to point out that all of this is super janky terrain that doesn't look very good if you dig into it. But the environment in Bloodborne is still stunning, and that's because they have really good art direction and technical design, not because they have super heavily subdivided terrains. So if done properly, myth number 3, if done properly, optimizations should be invisible even to you. That's definitely not the case, because rule number 5 is, if you can't tell you optimized it, you didn't optimize it enough. Draw calls. So draw calls are basically just sending models from the CPU to the GPU. They're very slow because the CPU doesn't do its business very effectively. Meshes times the number of uses, times the number of materials, times the number of shadows will usually give you a good idea of how many draw calls you have. So for example, right now I have these models here where each of them have 3 materials on them. There's 100 uses. This is a little messed up on the slide. But basically, 100 uses of these ends up being 600 draw calls once it's rendered. If all of them had been a single material, it would have been 200 draw calls. So you can see how that steps really rapidly. So never let scene objects have multiple material IDs unless they're using a skin, hair, or some other type of shader where it would make sense to break those up. Here's an example of a material that could be optimized. So you could actually take these 3 pieces, combine them into one object and one material. You can also do the same thing for like this. We have these ceiling pieces with several different crisscrossing patterns. You could combine those together into that box there, and then basically layer that out for the same visual but be more optimal. You could take things like this, where you have containers on shelves, and just combine them into a single object, where all of the configuration is basically set up together. And then you can even, in cases where, say, you have a box that you can open, rather than taking that box and putting a lid on it, you actually combine the lid and the box into a single model, so that you don't have to render 2 objects, and then only use the 2 when you have to. So texture atlasing is very useful, extending off of that. I think I'm probably running a little short on time, but I'll try to wrap this up quickly. So now one thing, both Unity and Unreal have the ability to do instant stereoscopic rendering, and that gives you the ability to basically take the information from one eye and render it the same for the other eye, rather than having to do more CPU calls. There are some situations where this actually can hurt your performance, but in general, I would say do it. In lighting, you want to make your lighting static, if at all possible. Baked lighting is always preferable. Dynamic lighting is terrible performance, and it actually increases both the draw calls and the poly count of your final scene. And it's roughly equivalent to the number of objects that it hits with those dynamic lights. So rule number 7, make your light static unless you absolutely cannot do it. Forward versus deferred rendering. Basically, this is a weird topic, but a lot of modern engines have shifted to being deferred. Deferred is actually kind of bad for VR because it's not quite as optimal, and you can't take advantage of the features that deferred rendering offers. So you want to use forward if at all possible. It allows you to do MSAA and a few other things. So rule number 8, use forward rendering. 5, post effects. There's an image without post effects. There's an image with way too many post effects. You want to find yourself somewhere in the middle. Post effects can take 1 to 3 milliseconds to render each. So some that are good are tone mapping, bloom, color correction, and fog. Everything else we probably shouldn't be using, both because it looks bad in VR and because it's bad for performance. So use as few post effects as possible. And I would say a lot more, but I know we're running short on time. So thank you guys.
We've
We have time for a question. Or...
got time for one question.
Any questions?
If anyone's got a question. Otherwise, you can obviously grab Tristan after. So we can power through then.
All right. Thanks.